I would like to demonstrate how to use a colored Petri net to cause a token in the input state to go to only one of two or more output states. And this is not the normal way that the Petri net would work. Normally, tokens are copied to both output states. If the transition can fire, we have the transition in the middle here, if it can fire, a token on the input state will be copied to both output states. Or, if there's no parameters on this, then a token will appear in both. So how do we get it to go to only one? We want to model a choice. In this case, I want tokens containing the text disk failure to move down into the state disk failure, and those containing server stopped to move into server stopped, so that we can model contingency plans. This is achieved by replacing the transition with a sub-Petri net, and a Petri net in itself. If we have a look at that internal Petri net, this is what it looks like. It actually has two transitions. So tokens in the incoming state, in the input state, shall go one or the other route. One of these two transitions will fire. If we put no guard expressions on them, then it's a random choice which one could fire. However, we've placed guard expressions on here saying that this one can only fire if the token on the input state contains the text disk failure. This one can only fire if it contains the text server stopped. So as a result, if we run, you see server stop went down here and disk failure went down there. It's reset it. And we watch it in the main one here. I'll start it again. Watch this. These two will go to the correct lower states. Boom, boom. Both transitions fired. It looked like it went through one transition, but actually internally there were two. This is modeled quite simply with this bit of code. Here is the code, the CPN code for modeling the overall network, and you can see that we have a incoming state which is called failures, containing server stopped, which is ready after 1 second, and disk failure ready after 5. Then we've made two output states based on an array called token matches, one for the disk failure, one for the server stopped, and these are laid out in a certain position separately based on X, and internally we've mapped this to a prototype called switch, which we loaded from the token switch component. Now here's the important part. These token matches are passed in with a special key called token match into the token match switch. So we've told the token match switch to build itself based on two matches. So in effect we've created one that will match one of these for the one output state and one of these for the other. If we have a look inside the token match switch component, you'll see how complicated that is, because token match is only one of the many configuration options we've allowed for this. Let's have a look in that briefly. We have some instructions on it, but most importantly, have a look at all of these options that we can configure. We can configure token match, expressions to match. By default it will look if the token match text is in the token, which is what we used before. This is an expression which is applied to each of these things. However, you can override those with individual expressions for each of them as well. You can also rename the states. Instead of input-output states, you can rename the input down here. You can also rename the output states, and you can even rename the transitions. The example that we've used here is, of course, much simpler. Doesn't use all of those options, it only uses these two pieces of text, so it defaults to a relatively simple case. In the next video we'll show a full contingency plan that demonstrates a much more comprehensive model, and also we wrap this Colored Petri Net syntax here with a contingency plan syntax that is a lot easier to understand if you're thinking in terms of contingency plans.